When a sound source, such as the siren of a fire truck, approaches you at some speed, passes by, and then moves away from you, the pitch of the sound decreases. The pitch is the subjective interpretation of the frequency as sensed by your ears and processed by your brain. So we can at least agree that the observed frequency lowers as the fire truck passes by. Something similar, but less familiar, occurs when an observer moves toward or away from a stationary source of sound. For instance, you may have observed such an occurrence as you ride in a car and pass by a stationary sound source such as a car horn. Such phenomena were first identified in 1842 by the Austrian physicist Christian Doppler and are collectively referred to as the Doppler effect. To explain why the Doppler effect occurs, we will bring together concepts that we have discussed previously, namely the velocity of an object and the wavelength and frequency of a sound wave. We will combine the effects of the velocities of the source and observer of the sound with the definitions of wavelength and frequency. In doing so, we will see that the Doppler effect is the change in frequency or pitch of the sound detected by an observer because the sound source and the observer have different velocities with respect to the medium of sound propagation. To see how the Doppler effect arises, first consider the sound emitted by a siren on the stationary fire truck, as seen here. Like the truck, the air is assumed to be stationary with respect to the earth. Each solid blue arc in the drawing represents a condensation of the sound wave. Since the sound pattern is symmetrical, listeners standing in front of or behind the truck detect the same number of condensations per second and, consequently, hear the same frequency. Once the truck begins to move, the situation changes. Ahead of the truck, the condensations are now closer together, resulting in a decrease in the wavelength of the sound. This bunching up occurs because the moving truck gains ground on the previously emitted condensation before emitting the next one. Since the condensations are closer together, the observer standing in front of the truck senses more of them arriving per second than she does when the truck is stationary. The increased rate of arrival corresponds to a greater sound frequency, which the observer hears as a higher pitch. Behind the moving truck, the condensations are farther apart than they are when the truck is stationary. This increase in wavelength occurs because the truck pulls away from the condensations emitted toward the rear. Consequently, fewer condensations per second arrive at the ear of an observer behind the truck, corresponding to a smaller sound frequency or lower pitch. Just to be clear, the speed relative to the air of the sound emitted from the moving truck does not depend on the speed of the truck or on the direction in which it is emitted. All that changes are the wavelengths and the corresponding frequencies of the sound waves. If the stationary siren in the drawing emits a condensation at a time t equals 0 seconds, it will emit the next one at a time t, where t is the period of the wave. The distance between these two condensations is the wavelength of the sound produced by the stationary source. When the truck is moving with the speed vs, where the subscript s stands for the source of the sound, toward a stationary observer, the siren also emits condensations at t equals 0 seconds and at time t. However, prior to emitting the second condensation, the truck moves closer to the observer by a distance vst as shown. As a result, the distance between successive condensations is no longer the wavelength lambda created by the stationary siren, but rather a wavelength lambda prime that is shortened by the amount vst. That is, lambda prime equals lambda minus vst. Let's denote the frequency perceived by the stationary observer as FO, where the subscript O stands for observer. The observed frequency, FO, is then equal to the speed of sound, v, divided by the shortened wavelength, lambda prime. With lambda prime equal to lambda minus vst, we write FO equals v divided by lambda prime, which equals v divided by lambda minus vst. But for the stationary siren, we have lambda equal to v divided by fs and t equal to 1 divided by fs, where fs is the frequency of the sound emitted by the source, not the frequency FO perceived by the observer. With the aid of these substitutions for lambda and t, the expression for FO can be written to give FO equals Fs times 1 divided by 1 minus Vs divided by V. This is the frequency observed for the case of a sound source moving toward a stationary observer. Since the term 1 minus Vs minus V in the denominator is less than 1, the frequency Fo heard by the observer is greater than the frequency Fs emitted by the source. When the siren moves away from rather than toward the observer, the wavelength lambda prime becomes greater than lambda according to lambda prime equals lambda plus Vst. Notice the plus sign in this equation where we had a minus sign for the source moving toward the observer. A similar analysis gives the result Fo equals Fs times 1 divided by 1 plus Vs divided by V, where now the denominator is greater than 1, and therefore the observed frequency Fo is less than the frequency Fs emitted by the source. In both cases, the difference between the two frequencies, Fo minus Fs, is called the Doppler shift, and its magnitude depends on the ratio of the speed of the source, Vs, to the speed of sound, V. Now let's consider a stationary source and moving observer. The drawing shows how the Doppler effect arises in this case. As in the case of the moving source, we assume that the air is stationary. The observer moves with a speed Vo, where the O stands for observer, toward the stationary source and covers a distance Vot in a time t. During this time, the moving observer encounters all of the condensations that he would if he were stationary, plus an additional number. The additional number of condensations encountered is the distance Vot divided by the distance lambda between successive condensations, or Vot divided by lambda. Thus, the number of additional condensations encountered per second by the moving observer is Vo divided by lambda. Since a stationary observer would hear a frequency Fs emitted by the source, the moving observer hears a greater frequency Fo given by Fo equals Fs plus Vo divided by lambda, which equals Fs times 1 plus Vo divided by lambda Fs. Using the fact that V equals lambda times Fs, where V is the speed of sound, we find that Fo equals Fs times 1 plus Vo divided by V. This is the frequency observed by an observer moving toward the source. An observer moving away from a stationary source moves in the same direction as the sound wave and, as a result, intercepts fewer condensations per second than a stationary observer does. In this case, the moving observer hears a smaller frequency that is given by Fo equals Fs times 1 minus Vo divided by V. It should be noted that the physical mechanism producing the Doppler effect is different when the source moves and when the observer is stationary from when the observer moves and the source is stationary. When the source moves, the wavelength of the sound perceived by the observer changes from lambda to lambda prime. When the wavelength changes, the stationary observer hears a different frequency, Fo, than the frequency produced by the source. On the other hand, when the observer moves and the source is stationary, the wavelength lambda does not change. Instead, the moving observer intercepts a different number of wave condensations per second than does a stationary observer, and therefore detects a different frequency, Fo. It is possible for both the sound source and the observer to move with respect to the medium of sound propagation. If the medium is stationary, all of our equations can be combined as follows. Fo equals Fs times 1 plus or minus Vo divided by V divided by 1 plus or minus Vs divided by V. The numerator accounts for the motion of the observer with respect to the stationary medium, and the plus sign applies when the observer moves toward the source, and the minus sign applies when the observer moves away from the source. The denominator accounts for the motion of the source with respect to the stationary medium, and the minus sign is used when the source moves toward the observer, and the plus sign is used when the source moves away from the observer. The symbols in this equation, Vo, Vs, and V, denote numbers without an algebraic sign because the direction of travel has been taken into account by the plus and minus signs that appear directly in this equation. Finally, this equation accounts for the concurrent motions of the observer and source, but you should keep in mind that Vo and Vs are measured relative to the medium in which the sound travels.